Good morning. Today is May 30th, 2024. This lecture is about electromagnetism. In particularly, we're going to be talking about electric flux. So, what is the electrical flux? Let's say if we have a plane with the area of A, and then we have electrical field passing through it. The electric flux, which is the phi E, is defined as the following. It is dot product. The little dot right here, that's called dot product of two vectors. One is your electric field, another one is the area. Okay, before we dive deeper into this, let's review a little bit about the dot product. So if we have a vector, let's say this is the A, another vector is B. By the way, the difference between vector and scalar is scalar just a regular number, for instance, 1, 2. But the vector not only have the number, but also have the direction. Notice we had an arrow right here. Right? And then when we write on vector, typically we put a little arrow on top of the letters and reminding us the A is not simply scalar. It has direction, so that's why A is vector. So if a vector A dot vector B that actually equal to the magnitude of A times magnitude of B times cosine theta, where theta is the angle between those two vectors. And then typically the magnitude of A, we use the same letter A but without the arrow. Similarly, B is the vector, the magnitude of vector B, and then cosine theta. Notice this is the scalar, and then this is also a scalar, and then cosine theta is also a scalar. So in other words, we started with two vectors. After we had the dot product, it ends with a scalar. So that's something you have to pay attention. Okay, so with that understanding, let's try to look at this definition right here. E, we already talked about it. That's the electric field. But A, I want to remind a little bit. So if this is the plane A or circle A, then the direction of A actually is the normal vector, which we typically put in half. This is the perpendicular to the plane. So in other words, when we have a plane, the direction of the plane is perpendicular to the plane itself. For instance, if we have a plane A like that, then the direction of the plane is going to be perpendicular to that. Okay? So, in order to understand this better, let's working on a specific problem. Let's say we have a circle like that, and then that circle have a radius r, right? And then the r, let's say, is equal to 0.2 meters. Okay, so we got an electrical field passing through it. Okay, that E actually is equal to 5 times 10 to the point 10 to the power of 3 Newton per Coulomb. Okay, so, and then the direction, sorry, I drew this as a radius, but the direction also in this direction as well. The direction, let's use a different color of the pencil. The direction of the plane and the direction of E, they form an angle called theta, where the theta equal to 60 degrees. So now I want you to tell me what is the electrical flux in this case. So we know by definition phi E equal to E dot A, right? And then that is the magnitude of E times the magnitude of the A, and then times cosine theta. Indeed, the magnitude of E we can write it as E without error, A without error, cosine theta, right? So the E, this actually in the x direction. So that's why you put an I hat right here. But if we're talking about E, we're just talking about the magnitude right here. So that will be 5 times 10 to the power of 3 Newton per Coulomb. What about A? A is the area of the circle, which is pi r squared, right? And then cosine theta, it would be the angle between the direction of the plane and the direction of the electrical field. So that is 60 degrees, right? That's what we have right here. We know R is 0.2, by the way, to be consistent, that's capital R. R should be 0.2 meters. So let's plug in the number again, 5, 10 to the power of 3 Newton per Coulomb times pi times R, which is 0.2 meter squared, times cosine 60 degree. So the trick identity is cosine 60 degree is equivalent to sine 90 degree subtract 60 degree. What does that mean? Let's say if we have a triangle like that, this is the 90 degree. If this is our theta, right? Theta equal to 60 degree. Notice the sum of the or interior angle of the of a triangle is equal to 180 degree, right? So that's x. That's the same. We try to looking at the angle x plus 60 degree plus 90 degree equal to 180 degree. So if we subtract 90 from both sides, we will get angle x plus 60 degree equal to 90 degrees. So angle x equal to 30 degrees. So cosine this, let me see, BC. So cosine 60 degree, that is this length BC over the hypotenuse AB. Now if we look at the sine 60 degree, is the opposite length, which is BC over the hypotenuse, which is AB. Notice those two expressions are the same. So that's why cosine 60 degree is equal to sine 30 degree. Okay? So we have 5 times 10 to the power of 3 Newton per Coulomb times pi, which is 3.14, times 0.2 will be 0.04 meter square, times sine 30 degrees, which is half, right? Times half. So this cancel out, we have 0.02, and 0.02 times this, we will have so 5 times 2, we got a 10. That would be 0.10. We still got a 10 to the power of the 3. So actually that's 100. So 100 times this, that will be 314 Newton meter square per coulomb. Okay, so that's our electrical flux in this case. So again, I want you guys to remember this, and then still the same problem. If we change this a little bit, if we have a case like that, we basically, this is our plane, right? It's tilted. Now we move perpendicular to the electric field. So the electric field, this is our E, is going to be perpendicular to the plane A. So we know the direction of A, which is, let me use different color, that's n hat, that's also perpendicular to the plane. In other words, the theta, which is the angle between the plane and the electric field E, is the same, right? So the theta is going to be equal to 0 degree. Okay, so in this case, what is the electric flux equal to? That equal to, again, by definition, E dot A, which is the magnitude of E, the magnitude of A cosine theta. We can rewrite it as E, which means magnitude because we don't have arrow. A is, again, we're talking about the area without arrow times cosine 0 degree, right? Because the angle is 0 degree. Now, before even plug in the detail, let's look at the cosine 0 degree. What is cosine 0 degree? So cosine 0 degree equal to 1, right? So this indeed is A dot, E dot A. So what is our E? Look at right here. Our E is 5 times 10 to the power of 3 Newton per coulomb. What is our A? We know A is, we know R is that, right? So that times pi R squared. So again, I'm going to write down as the following: 5 times 10 to the power of 3 Newton per coulomb times pi is 3.14 times R squared, which is 0.2 meter squared. And then that will be 5 times 10 to the power of 3 Newton per coulomb times 3.14 times 0.04 meter squared. Now we know 5 times 4 is 20, so this one to here, that will give us 0.2, right? And then we got 10 to the power of 3 times 0.2, that will give us 200. So 200 times 3.14, that gives us 628 Newton meter square per coulomb. So that's for that case. Now the next case that we want to go over is, what about if we have a plane like that, and then still the same electric field, and then if we look at the direction of the plane, that's that direction, that's n hat, so that actually is perpendicular to the direction of E. By the way, this is so in other words, A is perpendicular to E. So that derives to the following. The angle theta between A and E is indeed a 90 degree. So what is the electrical flux in this case? That is again by definition E dot A, and then that will be magnitude of E times magnitude of A cosine theta, which is the same as E dot A cosine theta, which is the same as E dot A cosine 90 degree. So we understand cosine 90 degrees, that's 0. So without even plugging any number into E or A, we know the whole thing is 0 because anything times 0 gives us 0. Okay, that pretty much covered three basic cases for the electrical flux. For the different geometric shape, all you need to do is calculate the area accordingly. If the E is variable E, then you have to use the integration and then a lot of technique to find the electric field. Electrical flux. But the basic idea is E dot A. And then also remember, electrical flux is the scalar. Even though they started with the dot product of two vectors, but indeed the final result is a scalar. Okay, so that's all I would like to share with you today. Feel free to leave the comments if you have any questions or any area you want me to reteach it. Thank you. Talk to you guys next time. Bye-bye.